Hey guys, Ms. Marusik here, and in this video we're going to talk about calculating enthalpy using bond energy. So this is just another method that I can use to solve the heat change of an overall reaction, just like we did with stoichiometry and with Hess's law and with heats of formation in our previous videos. Here what we'll be given are some bond energy data, and from that data we can actually calculate an approximate value for the delta H of our overall reaction. So we need to kind of go back for a moment and kind of recap exactly what bond energy is. So as a reminder, it says here that bond energy is the energy required to completely separate 1 mole of a covalent bond into its elements. So we're going to be doing this process for covalent bonds in reactions. We are not going to be doing this for reactions that contain ionic bonds. By the way, another term that we can use for bond energy would be bond enthalpy. Those mean exactly the same thing, and depending on which textbook you look at will depend on which of those terms you see used. When we talked about bond energy way back when, we looked at this graph here. So to kind of recap what this is trying to show, when I start off with my atoms really far apart, they have no attractions. But if I start to bring them closer and closer together, eventually they're going to start to sense each other, and they're going to start to form those attractions. And as they do so, what's going to happen is that the potential energy is going to start to drop. Now remember, as potential energy drops, that energy has to go somewhere, and so it's going to get transformed into kinetic energy that would get released into the surroundings. So as that bond eventually forms and those atoms come together, all of that energy would be released or freed when the bond forms. And we reach a point where it's kind of got an ideal circumstance here where attractive and repulsive forces are perfectly balanced, and whatever dip in energy occurs at that point is considered the bond energy. So for example, this graph is for diatomic hydrogen, and we notice that that occurs at negative 432 kilojoules per mole. So that means a 432 kilojoules for every 1 mole of diatomic hydrogen would get released as that bond forms. Now, if I wanted to break that bond, I would need to put in that energy to separate that attraction back apart. Also at that point, we have our ideal length where attractive and repulsive forces are balanced, and that refers to the bond length. So for example, here for hydrogen, the diatomic hydrogen has a bond length of 74 picometers. Now, what the other side of this graph is trying to show is that if I wanted to push these any closer together than they already were, I'm going to be fighting repulsive forces, and so I would have to put in a lot of energy to try and bring those any closer together. To be perfectly honest, we're not ever really concerned with that side of the graph. We're always concerned with this side where we're pulling things apart or trying to let them come back together. So, to kind of recap here, some other things we talked about with bond energy. It says here that an increase in bond energy, meaning the more energy it takes to separate this, that is indicative of stronger attractive forces, and so therefore we had a stronger bond to begin with. And this is going to tie back to our infamous Coulombic forces, our Coulomb's law. When I'm trying to think about having a stronger bond or stronger attractive forces, those forces are going to be impacted by the number of shared electrons and by internuclear distance. So on our shared electrons, the more shared electrons I have, the stronger that attraction will be. Also, if the internuclear distance is shorter, so as distance decreases, that too would increase my attractive forces and create a stronger bond. And with internuclear distance, really what we're thinking about there are your number of occupied energy levels in your individual atoms. Those are what impact the internuclear distance that these would have. So like, for example, this length in diatomic hydrogen is pretty short because they only have one occupied energy level, which is part of the reason that this bond is pretty strong, even though it's only a single bond with 2 shared electrons. Now, as we've already talked about, when a bond breaks apart, your Coulombic attractions must be overcome. They must be broken. And that requires an input of energy. Okay, so what I would need is kinetic energy to be gained by that bond, meaning our process is endothermic to split it apart, and our energy value should be reported as a positive. If the bond is forming, meaning I'm letting these come back together, what that will do is release our kinetic energy. So the process is exothermic and we would have a negative value. That goes back to that takes to break, freeze to form idea. So the way this is going to work is the fact that we're going to be given all of this data for our bond energies. And so what we're going to need to do is decide for a reaction, which bonds are we breaking and which bonds are we forming. And so for any bonds that are breaking, those energy changes would have a positive value for them because it takes to break, whereas any bonds that are forming would have a negative value because we free when we form bonds. So here's the deal. There is not a formula for this on our formula chart. So we are going to have to really decide how to approach these equations. So keep that in mind. This is not on the formula chart. Something else I want to call your attention to is the fact that when bonds break, typically we do that on the reactant side. We break all the reactants apart and then we form all of the products. So this is a reactants being positive and a products being negative scenario. You notice this is very different than heat of formation where it's products minus reactants. So we have to be really careful because we can't use that heat of formation equation here. We're going to have to kind of think about this from a different perspective. Also, I do want to mention down here that this only gets an approximate value for the delta H of the reaction. And the reason why is that when I'm given a bond energy data table, it in no way indicates what state the substances are in. It doesn't indicate the shape of the molecules, which can sometimes increase or decrease those energies. And it doesn't take into account the fact that I might need to also break and form different IMFs. And so therefore it only gets us an approximate value. And so sometimes it may or may not match up with the delta H reaction value that's a standard on a given table. It's only going to get us an approximate value here. Now, here's the one issue. If I'm trying to figure out which bonds are breaking and which ones are forming, I kind of need to see what type of bonds I have present. And I need to see if those bonds are double or triple or single, meaning I'm going to have to draw the structure of these. So we are going to be drawing Lewis structures in order to figure this out. And I know some of you are thinking, man, it's been a while since I've done Lewis structures. I know. So we're going to have to kind of remember how to do all of that within the context of doing these types of problems. You're still going to have to remember how to draw Lewis structures. All right, let's go ahead and switch the page and look at our first example here along with the table that we're given. So you notice we have this big, huge table of average bond energies. And again, they're an average because in some molecules, those may be different depending on the shape of the molecule or depending on what state it's in. There's all kinds of things that could affect these. So again, we are dealing here with just an average of these values, but it's still going to get us pretty good results. Okay, you notice that it only includes covalent bonds, and so therefore we're not going to be doing this process again for ionic bonds, so you're not going to have to worry about that. So it says here, using the bond energy table, calculate the approximate delta H of the reaction for the combustion of ethene, C2H4. Now the first thing you would want to do is get yourself a balanced reaction. So if I already had a balanced reaction, then I could just use that. If I don't have one, then I'm going to need to write one. And so that's what I went ahead and did here. Is I went and wrote myself, hey, C2H4 plus my oxygen yields CO2 and H2O, and I went ahead and balanced it utilizing coefficients. Now you notice I didn't worry about putting states here, and that's because as I'm doing these with bond energies, I'm not going to be able to take states into account. So you're not going to have to worry about that. So the next thing I want to do is I want to figure out what kind of bonds are present here. Are they single, double, or triple? What's happening? And so the next thing I would do is to draw a Lewis dot structure for each of these compounds. Now I hope you remember how to draw Lewis dot structures. I'm just going to go ahead and put my structures up here for these substances. So you can see I kind of did each in a different color, so that way you could follow along with what I did for each one. So here's the C2H4. Here's the 3O2. Now, instead of drawing it 3 times, I just put a 3 above it to indicate that I would have that structure occurring 3 times. Same thing goes for the CO2 and the H2O. Those two structures are each occurring twice based on my coefficients, and so I just put those coefficient values above those structures instead of drawing it twice. All right, so the next thing I would do is for each of these compounds, I would list off what kind of bonds I have present, and then also indicate within that if they're single, double, or triple. And then I would put if that bond is breaking or forming. Now think about this for a minute. I always have to break everything apart before I can reform it back together. So anything on that reactant side is going to get broken, and anything on that product side is going to get formed. And so here is my list that I came up with for each of these substances. I can see in the ethene that I have one double bonded carbon to another carbon, and then I have 4 single bonded carbon to hydrogen bonds. So you can write carbon to hydrogen or hydrogen to carbon. It really doesn't matter. Here in the oxygen, I had a double bond, but don't forget I had 3 of those molecules. So I put 3 double bonded oxygens. And you notice with both of those, I wrote that I'm breaking those because they're on the reactant side. On the product side over here, I had my 2 carbon dioxides that each had 2 of the oxygen to carbon bond. So that gives me a grand total of 4 of those bonds. And then here in the water, each water had 2 of the oxygen to hydrogen bond, but because there were 2 molecules, that would give me a total of 4 of that single bond. Again, notice on the product side, I wrote form. So now what I would need to do is look up data for each of these types of bonds in my table up above. Okay, so I will point out really quick up here, just a couple kind of things. If you notice, like for example on the water, you had an oxygen to hydrogen bond, and you might have written it as hydrogen to oxygen. So if you look in the hydrogen section and you don't see hydrogen to oxygen, then you can always go to the oxygen section and find the oxygen to hydrogen bond. It's the same exact thing, and so then that would get you your value for the energy associated with that bond. I also want to show you that over here on this side, we have our multiple bonds. So if you have a double or triple bond present, then you may need to use one of these. Now, one other thing to call your attention to is that the carbon to oxygen bond has a star with it. And you notice there that that has a particular value. But if you notate the star down here, it gives us an alternate value for that double bonded carbon to oxygen. This is the bond energy that I would use if the carbon to oxygen is specifically in CO2, which for this example, it is in CO2, and so I'm going to need to use that. But if the carbon to oxygen bond was in anything else other than CO2, then I would use this value here. That increase in energy that we see here has to do with the shape of that molecule. Typically, when I have a carbon to oxygen bond, I have smaller bond angles, but with CO2, because it's linear and my bond angles are 180, that affects the bond energy values within that particular structure. Okay, so coming back down here, here's how I would approach this. I'm going to start kind of listing everything off number-wise. So you notice I started off with the carbon to carbon bond. There was one of it. It had a value of 614 up on the table above, and I put a positive with it because it takes to break. On the next one, I had 4 carbon to hydrogens, and so the carbon to hydrogen had a bond energy of 413. Again, I put a positive with it because I broke it. So then once I'm done with C2H4, I can move on to the O2. Here I had 3 of those diatomic oxygen bonds that I needed to break that were double bonds, and so that bond energy was 495. I did put a positive with it again because I'm breaking it. But then when I transition over to the product side, you notice with these, I'm putting negatives. So for every carbon to oxygen double bond within CO2, I'm going to use that special value at the bottom of the table of 799. And then again, there were 4 of those bonds. And then for the H2O, that had a value of 467 for the oxygen to hydrogen. And there were 4 of those bonds. So again, I put those negatives there because when I form those bonds, I release that energy. And so then once I get all of that, basically all I do is just total everything up. And when I total everything up here, that gets a value of negative 1313 kilojoules, and that would be per mole of the reaction. Now you notice this value did come out to be negative, and I want to talk about what that means for a minute. We had all of that energy that it takes to break, and all of the energy over here that we released when we formed. And remember, the takes to break energy was all positive, and the freeze when I formed was all negative. If this overall heat of the reaction comes out negative, what that must mean is that the energy I released when the bonds reformed must be greater than the energy it took to break them. So it's like I put in a little bit to break them, and then I released a whole bunch when it formed. And if I think about that, that makes sense for a reaction that has a negative delta H, because that would be indicative of being an exothermic reaction with our potential energy diagram that looks something like this. I put in a little bit and I get a lot out of the deal. I only needed a little bit of energy to break, but I released much more when those bonds reformed. All right, here's what I want you to do. There is a problem on the top of the next page. They even did you a favor and gave you the balanced reaction for it. So what I want you to do is to take a moment, pause this video, and see if you can solve this problem. All right. Did you pause the video? Did you try it out? Hopefully you did. Let's see how it came out for you. Here's what I got from start to finish. Now, I will tell you this, as you can see, it's really important that you draw your Lewis dot structures correctly, because if you draw those incorrectly, then that can get you wrong values for your heat change. If I didn't realize that this had a triple bond, then I wouldn't use the correct energy down here in my calculation. So what you should have had is that you are breaking one triple bonded nitrogen to nitrogen bond. We are also breaking 3 fluorine to fluorine single bonds, and that's because I had 3 of that molecule. And then when I get over here, each of these NF3s had 3 of the nitrogen to fluorine bonds, but then I noticed that I had 2 of those molecules. So that gives me a grand total of 6 of that particular bond. And so then I would go look up my values on my bond energy table. Typically they give you that table, a modified, smaller version of it within the context of a question. So they won't give you that whole thing, they'll just give you a smaller version. And then I used all those values multiplied by their coefficient, because again, those are a kilojoules per mole of that bond, and so we need to address how many moles we have. And you notice for the ones that I broke, I put a positive, and the one that it formed, I put a negative. And when I totaled that, that got a value of negative 229. And as far as my unit, it's kilojoules per mole of the reaction. So now I know this is exothermic. I know overall this reaction would feel hot. I know that the temperature would increase. I could use this in a stoichiometry problem. All kinds of things. However, I will tell you this, don't forget that this is an approximate value. It mentions that up here. So if you actually looked up the delta H value for this reaction, say on a standard table, you may notice that the heat might be a little bit different. Again, this does not take into account states. It doesn't take into account IMF changes. It doesn't take into account the shape of the molecule. So there's all kinds of things that could play a role here. All right, we have one last problem at the bottom. This one's a little bit different because on this one, what they want us to do is to actually approximate a bond energy value. So they give me some process that's happening here. So they give me some reactants and they give me a product that I'm trying to make. They give me some of the bond energies, and then they give me the delta H of the overall reaction. Now, I know some of you are thinking, okay, wait a minute, Miss Marusik, don't I have that bond energy value on the previous page? Couldn't I just look up the carbon to nitrogen bond myself? Well, the problem is that this particular question was actually on the AP test, and they did not give them a bond data table that had all of those values on it. And so you actually had to use your brain on this one to figure out what was happening. Now, here's the deal. There's lots of bonds happening in here. And if I had to do all of that math, that would get really annoying really fast. But I noticed that not all the bonds broke and reformed in this process. I noticed that some of the bonds over here look exactly the same as the bonds on the other side. I mean, look at this part of my structure here. I see that same exact part to the structure on this side. I also see that there's quite a bit of this structure that remained intact. All of this part of the structure remained intact on this other side. So if I really pay attention to the things that specifically changed, I noticed that I had all of these bonds, this guy, and this guy, breaking. And then I ended up forming this peptide bond, which might sound kind of like, I don't know, biology, right? And then I ended up forming the bonds in this water. Some of you might have even got really sneaky and realized that actually one of the OH bonds even remained the same as well. So that would even save your math a little bit more. So what I did next is I listed off what actually broke and what actually formed over here. So I noticed that the way I did this, I ended up breaking on this side a carbon to oxygen, an oxygen to hydrogen, and a nitrogen to hydrogen bond. And on the product side, I ended up forming that carbon to nitrogen bond and 2 oxygen to hydrogen bonds within the water. And so what I'm trying to do here is I'm trying to figure out the bond energy of the carbon to nitrogen bond. And so I'm going to set that bond as being X. If you notice over here, they actually give us data for all the rest of these bonds. And so then I would set up an equation just kind of like we did on those other problems. I would say, okay, well, all the bonds that I break would have a positive value for the energy of breaking that bond. So to break carbon to oxygen was 358. To break the oxygen to hydrogen was 467. To break the nitrogen to hydrogen, that was 391. But then to form my bonds, that would release energy. Again, freeze to form. And so in forming that bond here that I don't know, that would be a minus X, whatever that value ends up being. And then here I have 2 of those OHs, and the 2 OHs each would be 467. And so then I'm simply just solving for X. And so I would kind of work to solve my algebra. I'd probably like combine all of this math together, subtract off the 2 times the 467. That would get me a number minus X equaling positive 12. And so then I would just simply subtract all that math over and flip the sign, because obviously I don't want to solve for a negative X. I want to solve for a positive X. And so in solving for X, that gets a value of 270 kilojoules per mole of the carbon to nitrogen bond in this structure. Now, the reason why it was important to actually calculate this is if you look at the carbon to nitrogen bond value back on this table here, this actually has a value on the table of 305, which is a little bit different than the 270 we got here. But remember, those tables don't take into account the shape and the IMFs and the states. So we wanted to be very specific about what's going on with that peptide bond in this molecule specifically. All right, I hope we're feeling pretty good about calculating with bond energies. Remember, you've got to be able to draw those Lewis dot structures correctly, or it's going to totally mess you up as you're trying to calculate these values. If you have any questions or need any help, please feel free to email me. Bye, guys.